Alright, in this video we're going to be looking at Argand diagrams. So Argand diagrams are simply complex numbers being plotted on a complex plane. So you'll be given various equations and inequalities involving complex numbers, and you should be able to plot those equations and inequalities on a complex plane. So we're going to go through the different types of equations and inequalities that you can get and how you would go about plotting them. So the first equation that they can give you is an equation of the form modulus of z minus a is equal to k, where a is a complex number. This will be a circle with center A, and radius k. Let's look at an example. So say you're required to draw the Argand diagram satisfying the equation z minus 2 plus 3i is equal to 4. This is going to be a circle with our center is going to be 2, 3i, and radius 4. Our radius will be 4. Alright, so let's draw that. So we've got our imaginary axis and we've got our real axis. The center of our circle is 2, 3i, so 2 units in the real axis, that's here, and then 3 units in the imaginary axis. So the center will be right here. And we want to draw a circle with a radius of 4. So let's do that. So let me make sure that our center looks somewhat decent. I think that's better. Maybe slightly lower. Somewhere here. Yeah. Alright, so this will be the Argand diagram satisfying the modulus of z minus 2 plus 3i is equal to 4. This is a circle with center 2, 3i and radius 4. Now what I will emphasize is that this has to be strictly a negative sign. Say this was given as z plus negative 2, negative 3i, alright, and this is equal to 4. You would have to factor out that negative sign from your complex number so that it becomes z minus 2 plus 3i, okay, and here you then get the coordinates of the center of the circle. So it has to be strictly a negative sign. If it's a positive sign, factor out the negative sign. Now the next scenario that we can get is an inequality of the form the modulus of z minus a is less than k. Alternatively, it may be given as the modulus of z minus a is less than or equal to k, where a is a complex number. So we already know that this is a circle with center A and radius k. Alright, but what this less than sign means, it means that we want the area inside of the circle, right? So going back to our example above here, we would shade the region inside of the circle. This is the region that satisfies our inequality. But because it only says less than, it means that it doesn't include the circle itself. So your circle here shouldn't be a solid circle, but it should be dashed. So you should have a dashed circle to show that you only want the region inside of the circle, but you're not including the circumference of the circle. Alright, so this is for less than. If it's less than or equal to, now it means we want the circumference of the circle as well as the area inside of the circle. Alright, so that's the less than. And so if you think about it, if this is greater than, it means you want the area outside of your circle. If this is greater than or equal to, then it means you want the circumference of the circle and the area outside of the circle. Alright, now let's look at a scenario where we've got the modulus of z minus a is equal to the modulus of z minus b. Alright, where a and b are complex numbers, this means we have to bisect the line that connects a to b, and the region that would satisfy this equation is the bisector of that line. So let's look at an example. Say we're given z minus 2 minus 4i, and this is equal to the modulus of z minus 3 plus 4i. Alright, so this means we have to bisect the line that connects this complex number to that complex number. So let's first draw a complex plane. We've got our imaginary axis and we've got our real axis. And let's start by plotting the first complex number. So this is negative 2, negative 4i. So negative 2 units in the real axis, that's here, and then negative 4 units in the imaginary axis. Negative 1, negative 2, negative 3, negative 4 units are here. So our point will be right there. And then the other complex number is 3 plus 4i. So 3 units in the real axis, 1, 2, 3, and then 4 units in the imaginary axis. This is 3, this is 1, 2, 3, 4 units, so 4i. So that means our complex number will be here. Let's draw a line that joins these 2 points together. Alright, let's call this complex number A, let's call this complex number B. So the points that satisfy this equation are the points that are equidistant to A and B. So to get the points that are equidistant to A and B, equidistance means they are the same distance from A and from B. So to get those points, we have to bisect this line. I do not have a compass with me, but make sure to use a compass when you're bisecting your line. I'm assuming my bisector will come around somewhere here. Let's shift it towards the middle. Probably somewhere here. This looks roundabout correct. And you're going to have your construction arcs as well. Make sure to leave those on the paper. And make sure you're using a compass for this. I don't have a compass with me, but I just want you to see what it would look like. So the points that satisfy your equation are the points that are on this red bisector. What if the sign, instead of being an equal sign here, what if our sign was less than? So this would mean we want the points that are closer to A than B. So that's going to be points on this side of our bisector. So you shade this side. Alright, but notice that our sign here is less than, not less than or equal to. Less than or equal to this solution would be fine to show that we want points that are either the same distance from A and B or closer to A. So this would be fine. But if it's just less than and you don't have the or equal to part, it means that your bisector here should be a discontinuous line, not a solid line. So it's going to be a dashed line that looks something like this. Forgive me, I do not have a ruler with me, but make sure you use a ruler. And if this was greater than, then it just means we're going to shade the opposite side. It just means that we want points that are farther from A than B, or points that are closer to B than A. Then the next situation that we can have is this number 4. Yes, number 4. We're now looking at arguments. So you can have the arg z minus a is equal to a certain angle that will specify the angle, where a is a complex number. What this means is that you should draw a horizontal line going through your complex number and then open your angle theta with respect to that horizontal line. So from that horizontal line, draw the angle theta. So let's look at an example. So say you're given arg z minus 2 plus 3i is equal to a quarter pi. Let's draw a complex plane. we've got our imaginary axis, and we've got our real axis, and we're looking at the complex number 2 plus 3i, so 2 units in the real axis and 3 units in the imaginary axis. So our complex number is here. Let's draw a horizontal line. I'll make it dashed here, and we want to open the angle 1 over 4 pi from our complex number here. So use a protractor to open this angle of a quarter pi. A quarter pi is going to be 45 degrees if you convert this to degrees. So use your protractor to open up an angle of 45 degrees. Alright, so this here is going to be a quarter pi. So this red line is the one that satisfies our equation here. We want the region where the argument of z minus 2 plus 3i is equal to the angle a quarter pi. Alright, so the points where our argument is a quarter pi are the points on that red line. And now if they'd changed this sign and the sign was less than or equal to, it would mean we want this region over here, the region that is less than or equal to a quarter pi. So it's including this line as well as the area that's below that. Alright, if we remove this or equal part, it means that this line at a quarter pi must be a dashed line because we're not going to be including it. And if the sign is greater than instead of less than, it just means you want the region that is above that line and not below that line. Alright, so let's look at some past paper questions on Argand diagrams. Here we're given that on an Argand diagram, shade the region whose points represent complex numbers z which satisfy both inequalities z minus 4 minus 3i is less than or equal to 2 and arg z minus 2 minus I is greater than or equal to a third pi. Alright, so let's start with the first inequality here. We want to factor out a negative sign, so this becomes z minus negative 4 divided by negative 1 gives us a positive 4, and then that becomes positive 3i, and this is less than or equal to 2. So let's draw a complex plane. This is our imaginary axis and this is our real axis. So this is going to be a circle with center 4, 3i. So 4 units in the real axis, so that's 4 units, and then 3 units in the imaginary axis, so 3i. Our center will be over here, and we're drawing a circle with radius 2. So it's going to look something like this. Alright, so let's shift it so that it's at the center. Okay, that looks better. So this is the circle and we want less than or equal to. Alright, so that's going to be the area inside the circle, including the circle. For now, I'm not going to shade that region. Let's first evaluate this inequality and then we can shade the required region. So that's arg z minus 2 minus I is greater than or equal to a third pi. So we need to factor out the negative sign. So arg z minus, that becomes 2 plus I is greater than or equal to a third pi. So our point 2 plus I is going to be this point over here. So we're going to draw a horizontal line here. And we want to open an angle of 1/3 pi radians. So 1/3 pi is 60 degrees. So use your protractor to open an angle of 60 degrees. So I'm just going to estimate here, but make sure you use a protractor. So I'm assuming that 1/3 pi or 60 degrees is over here. And we want the region that's greater than or equal to, but it also has to be within our circle. So greater than 1/3 pi, but within our circle, that's going to be this region over here. Alright, so that's going to be our answer for part A. Part B says calculate the greatest value of arg z for points in this region. So we need to find the largest angle formed from the origin with this point. So the largest angle will go from our origin to somewhere here. So let's call this our angle theta, and we need to somehow find theta. We can find theta by splitting theta into two smaller angles. So first we can draw a triangle like this, and coming back to the origin, we've got a right angle there, and then we'll have another triangle which is going to come down to r is equal to 4, and it goes down to our origin. So the angle above, we can call it angle alpha, plus the angle below, let's call that beta. So these two angles should give us our argument. Alright, so we need to find alpha. Let's extract each of these triangles so that we see what's going on. So firstly, we've got the triangle that's above, and it looks like this. It's got a right angle over there. Now we can actually find the length of this line, which is the line from the origin to the center of the circle. The center of the circle, we know it has coordinates 4, 3i. So the length of this line is simply the modulus of our complex number. So the modulus of 4 plus 3i, and that's going to be the square root of 3 squared plus 4 squared. So that's going to be root 9 plus 16, which is root 25. So this gives us 5. So we know that the length of this line is 5. Then the distance from here to the circumference there is the radius of our circle. The radius of our circle is 2, so it means that this distance is 2. So to find angle alpha, we've got the opposite and we've got the hypotenuse. So we can say that sine alpha is equal to opposite, which is 2, over the hypotenuse, which is 5. So alpha is equal to arcsine of 2 over 5. And then we need to find beta as well. So let's extract its triangle. So it's the green triangle that we have, which looks like this. We've got a right angle here, which should be at this point here. The length of this line, our hypotenuse, we know that that's 5. And then the length of our adjacent is going to be 4. And the angle that we have here, angle beta, we can say that we've got the hypotenuse and the adjacent. So cos beta is equal to adjacent, which is 4 over 5. So beta is equal to arc cos of 4 over 5. And so it means that the greatest value of our argument, like we said, is the sum of these two angles. So arc z is equal to alpha plus beta. So alpha plus beta. So arc z is going to be, we're using the exact values, arcsine of 2 over 5 plus arc cos of 4 over 5. Let's punch this into the calculator. I will do this in radians, but since they haven't specified, you can be in either radians or degrees. So arcsine of 2 over 5 plus arc cos of 4 over 5. That gives us 1.06, correct to 3 significant figures. And that's the greatest value of arc z for points in this region. Let's look at another example. On a single Argand diagram, sketch the loci given by the equations modulus of z minus 3 plus 2i is equal to 2, and the modulus of w minus 3 plus 2i is equal to the modulus of w plus 3 minus 4i, where z and w are complex numbers. Alright, so we'll start by focusing on the first equation. The modulus of z minus 3 plus 2i is equal to 2. Let's factor out a negative sign from our complex number. So this becomes the modulus of z minus 3 minus 2i is equal to 2. So let's draw a complex plane. We've got the imaginary axis and we've got the real axis. And so what we have here is a circle with center 3, negative 2i, and a radius of 2 units. So 3 units in the real axis, 1, 2, 3, and then negative 2i in the imaginary axis, negative 1, negative 2. And so the center of our circle is going to be here, and our radius is 2 units. So our circle is going to look like this. So this satisfies this equation. Now let's look at this equation. That's the modulus of w minus 3 plus 2i is equal to the modulus of w plus 3 minus 4i. So let's factor out a negative sign in the complex number here. That becomes 3 minus 2i is equal to, let's factor out a negative sign here as well. So that becomes negative 3 plus 4i. Alright, so let's first plot both of our points. So the first point here, 3 minus 2i, is the center of our circle. Then the second point here, negative 3 plus 4i, that's going to be negative 1, negative 2, negative 3 units in the real axis, and positive 4 units in the imaginary axis. So 4i. So this point will be here. And let's draw a line joining our 2 points. So what this equation means is that we want the points that are equidistant to the complex number 3 minus 2i and negative 3 plus 4i. So it means we have to find the perpendicular bisector of our line. So make sure to use a compass to get your perpendicular bisector. I don't have a compass with me, so I'm just going to estimate that our perpendicular bisector should be somewhere there, maybe slightly lower. No, I think that was fine. Alright, and you should of course have your construction arcs, okay, but make sure you get these construction arcs from using a compass. So the blue circle, the circumference of the blue circle satisfies this first equation, and then the green perpendicular bisector satisfies the second equation. Alright, let's move on to part B. Hence find the least value of the modulus of z minus w for points on these loci. Give your answer in an exact form. So for the complex number z, the points that are on the loci that we want are the points on the circumference of the blue circle. And then for the complex number w, the points that we want are the points on the green perpendicular bisector. So they're saying find the least value of the distance between z minus w. So we want to find the least value of the distance from our perpendicular bisector to the circumference of the circle, and so that distance is the distance from this point to this point on our circle. So we need to find the distance of that line. Alright, so to get this distance from the circle to our perpendicular bisector, we need to get the distance from the center of our circle to the perpendicular bisector and then subtract the radius of our circle. So to get the distance from the center of our circle to the perpendicular bisector, that is going to be half the distance from this point to this point. So if we can first find the distance of the full length of the red line, then we can find half of that to get the distance that we want from the center of the circle to the perpendicular bisector. So the coordinates of the center of the circle are 3, negative 2i. And then the coordinates of this other point are negative 3, 4i. So the length of that red line is going to be negative 3 here minus the 3 there squared plus 4 minus minus 2, so 4 plus 2 squared. And let's punch that into the calculator. The square root of negative 3 squared plus 4 plus 2 squared, that gives us 6 root 2. So it means that the full length of our red line is 6 root 2, but we only want half of that line. The reason we want half of that line is because this green line is a perpendicular bisector, so it splits the red line in half, meaning the distance from the center to the perpendicular bisector is half the length of the red line. So half of 6 root 2 is going to give us 3 root 2. Alright, so it means the distance from the circumference of the circle to the perpendicular bisector, which is the shortest distance between Z and W, because all these other points would have a larger distance. It means that distance is going to be equal to 3 root 2, which is the length from center to perpendicular bisector, minus the radius of our circle, which is 2. So 3 root 2 minus 2, and that's going to be our final answer. Alright, so that's it for the Argand diagram video. Make sure to go through the quiz, and I'll see you in the next one.